Okay, so in this particular lesson, we're going to address two seemingly unrelated topics, but there is sort of a connection between them. We're going to look at solving equations that deal with higher orders, basically things that we can deal with factoring, and then we're going to look at solving radical equations, things that have square roots in them, and how one might address that. Okay. So to get started, whenever we want to solve an equation of this particular type, we want to set it up so that we can get the expression equal to 0. Then, if we can identify any kind of greatest common factor, or GCF, we want to go ahead and factor that out as well. All right, then, once we've done that, we want to look at what's left and make a decision about the types of things that we're dealing with. So, for example, if we see something that's got two terms in it, that means we're either dealing with a difference of two squares, which is a squared minus b squared, which factors into a minus b and a plus b, or we're dealing with the difference or sum of two cubes, which is a cubed plus or minus b cubed. So that's a plus or minus b, sorry, a plus or minus b. So obviously the sign is going to change depending upon what's between them. Then a squared minus plus, because the sign switches on that second term, ab plus b squared. So if you see two terms, you know it's some sort of factoring shortcut, or you're done at that point. If you see three terms, then either you want to try sort of the guess and check method of factoring. And if you see four terms, then, and I say at this moment, then we want to try factor by grouping. Later on in the course, we're going to look at some other techniques that will apply to that. Once we've identified that, then, kind of scroll down here. We want to make sure all factors are prime, and if they're not prime, then we want to go back and repeat the factoring pattern. Prime basically means I can't factor anymore. And then, once we've got them factored and we've got them all in prime form, then we want to set each factor equal to 0 and solve for the given variable. Okay, so let's take a look at our first example here, and let's go through our little process here. So looking at these terms, there's three of them, but do we see a greatest common factor, or GCF, that we can take out? Hopefully we see that, yeah, we can, let's see, 6, 22, and 8 all have a factor of 2 in them, and I at least can take out an x. Okay, so when I factor that out, see, 6x cubed divided by 2x gives me 3x squared, 22x squared, so that leaves me with 11x minus 4. Okay, so then I want to focus on that expression. So I know there's already a 2x out there, but looking at the 3x squared plus 11x minus 4, I'm trying to break it up into something like that. So I want to look at the 3, and what multiplies to give me a 3x? Well, that's 3 and 1, so it's either 3x squared. So it's 3x and x, or it's x and 3x, but that's pretty much it. And then to get the negative 4, it's either 1 and 4 or 2 and 2, and there's a negative in there somewhere, right? So kind of playing around with these numbers, let me get some more space here. I've either got a 1 and a 3, or a 3 and a 1, and I've got a 1 and a 4, or a 2 and a 2. So some sort of combination like that. So thinking out loud in my head, I know there's got to be a 3 in here, so that means I want to triple one of these numbers. And when I multiply by 3 and do some sort of combination of subtracting, is there any way to get an 11 out of that? Well, 3 times 2 is 6, and 6 and 2, well, 6 and 2 is, I either get 8 or I get 4, so that's not going to give me an 11. But what about this 3, 3 and 1? That's 3 plus the 4, that'll give me 7. How about the 3 and the 4? Well, 3 and 4 give me 12, and that gives me a 1. So is there any way a 12 and a 1 can give me an 11? Yeah, that's not that bad. So that means that my factored form has got to have, oops, get some more, try to get more space here. So it's got to have an x and a 3x, and I want to make sure that that 3 gets multiplied with the 4. So it's got to be the 4 and the 1. And then, I've got to check my signs here. So I want, when I multiply the 3 and the 4, I want that to be a positive 12, and I want that to be a minus 1. And there's a 2x there. Okay, so, and then I'll go back each expression. So 2x's, I've done factoring that, x plus 4, done factoring, 3x minus 1. So each of my terms is fully prime now. They're all, I factored as far as I can go, and then I just want to set each one up and solve for 0. So that's going to be 2x equals 0, x plus 4 equals 0, and 3x minus 1 equals 0. We'll divide that by 2. Over here we'll subtract off 4. Over here we'll add 1. So here I get x is 0. And then next door I get x is negative 4. This piece, this 3x equals 1. So when I divide by 3 I get 1/3. So it looks like all of my answers are 0. Since we're staring at them, I might as well put them in order. I got negative 4, 0, and 1/3 would be all of my answers in that. Okay, so in the second example, looking at 5x to the 4th minus 20x squared, again, try to identify a greatest common factor if we can. And I can take out at least a 5, and it looks like I can take out an x squared. And so when I factor that out, I'm left with x squared minus 4. Okay, now x squared minus 4, we're down to 2 terms. That's one of our special cases. That's an example of difference of 2 squares. So I can break that up even more as x minus 2 and x plus 2. Alright, then I can set each of my expressions equal to 0 and solve. So I got 5x squared equals 0. I've got x minus 2 equals 0. And I've got x plus 2 equals 0. Okay, so here if I divide by 5, that'll get that done. Here I want to add 2, and here I want to subtract 2. Well, if I get x squared equals 0, x equals positive 2, and x equals negative 2. Alright, the square root, this x squared equals 0, that's where I can apply the square root. And technically we do get plus or minus 0, but in reality 0 is not a positive or negative quantity, so we don't worry about the sign there. And so if I collect up all of my answers on this one, I get a solution set of negative 2, 0, and 2. Alright, so on this last one, we're going to look at all our numbers and make a decision about what to do. We got x to the 4th, we got 4x cubed minus 8x, and a 32. Well, there's not really a GCF we can take out. Like I can take x out of one side, but I've got to be able to do it to all of them. And so about the only thing I can think of to do is bring the 32 over. So x to the fourth plus 4x cubed minus x minus 32. And then that fits in one of our patterns. So we've got 4 terms, and that fits in the factor by grouping pattern. So in factor by grouping, I want to break them up into 2 sets of 2. So I want to look at the first set of 2 and the second set of 2. And what's the biggest thing I can factor out of the first set? Well, that's x cubed times x plus 4. And out of the second set, out of the minus 8x and the minus 32, I can take an 8 out of that. So that's minus 8 times x plus 4, of course, equals 0. Now, the nice thing about factor by grouping is if I do it correctly, those two expressions should match each other, and they do, so that means I did a good job. So I can bring out the x plus 4, and that leaves me with x cubed minus 8 equals 0. Okay, now at this point, let's look at what we have. We have x cubed minus 8. Well, it's 2 terms, so if it is factorable, it's got to be one of our factoring patterns, and it is. That would be the difference of 2 cubes, which means this expression should be, in other words, x cubed minus 8 is going to look like something cubed minus something cubed. Well, obviously x cubed, we cube x. What about 8 though? What do you cube to get an 8? That's 2. Okay, so using that factoring pattern of difference of 2 cubes, that would factor into x minus 2, x squared, plus 2x plus 4. And it might, honestly, it might just be a while since you've seen that type of factoring pattern. Okay, so let's put this together with what we've got so far. We have x plus 4 times x minus 2 times x squared plus 2x plus 4. Okay, now part of this is going to be really simple because x plus 4 equals 0 and x minus 2 equals 0. That we can do a quick job of solving and get negative 4 and a positive 2. But what about that expression? Well, I'm going to use a little bit more room to demonstrate that as far as what that solution is. So I'm going to come over here. Sorry, I need more room. Looking at what where I'm allowed to write. Okay, so x squared plus 2x plus 4. That's what I'm trying to solve for. Now, that's actually not factorable. It's one of the benefits of doing difference of 2 cubes is we end up with 2 expressions, both of which are prime. So we can't solve that by factoring, but we can look at the quadratic formula. So I can set a equal to 1, b is 2, c is 4, and then I can set that up. So negative b plus or minus the square root, b squared minus 4 ac all over 2a. All right, so then we'll simplify that down. So negative 2 plus or minus 4 minus 16 all over 2. Well, 4 minus 16 is negative 12. All right, so then we got to remind ourselves, how do we break 12 up? Well, the negative part means that we have an I on the outside, so I'm not too stressed about that right now. But 12, what you got to remember is 4 times 3, and that's 2 times 2. So within 12, I've got a pair of 2s, so I can simplify and bring a 2 on the outside. So that's negative 2 plus or minus 2i times the square root of 3 over 2. And in looking at all of those numbers, I can divide 2 out of everything. So that's -1 plus or minus I times the square root of 3. So that actually comes back and ends up as part of our solution set. And those would be all of our solutions, both real and imaginary. Okay, so the next topic we're going to continue with is solving equations that aren't quite factorable the way we see them, but they are something that looks like they're in quadratic form and allows us to use a concept called substitution. Now, I want you to take a look at these 3 problems, and I want you to pause the video and I want you to ask yourself, what do these 3 problems have in common? Because there's certain characteristics, and that's what this list of 5 off to the side here are. There's certain characteristics that these 3 problems have in common, and it's because of these characteristics that we claim that they are actually in quadratic form and allows us to use this idea of substitution. All right, so go ahead and pause it, and then I'm going to go through the list with you. Okay, so hopefully you had a chance to look. One of the first things that students point out is that in each case, it is some sort of expression equal to 0. Okay. Then they all point out that there's 3 terms in each case. We're dealing with 3 terms of each kind. Then gets a little on the creative side, so then hopefully they notice that there are constants. Oops. That the last term happens to be a constant in each case. So constant term at the end. All right. Then it gets a little on the creative side there. What about other things they notice? Some students will point out that, well, you know, when you look at the first and the middle, they all have the same base of some kind. So each variable and base is the same from the first and second term. And then, hopefully, when you look at the last things, kind of the one that really requires you to sort of think outside the box, when you look at the exponent, the middle exponent, if you double it, you get the outer exponent. So 2 doubled is 4, 1/3 doubled is 2/3, x plus 3, if you square that or double that, you get x plus 3 squared. So it looks like that the exponents of the first term is twice the exponent of the second. Okay, so it's this, and because of these 5 characteristics, then, that we are able to qualify these equations to be written in quadratic form.